Today, we are going to look into a couple of corner cases where some delicate features of the experimental setup can make us treat the factor as fixed rather than random, or vice versa. Consider the technique of blocking in experimental design. A blocking factor is introduced to explain some of the nuisance response variation. Oftentimes, blocking increases the precision, resulting in smaller standard errors and more significant p-values for the factors of interest. For example, a single level of blocking factor can describe a group of patients that are somehow similar to one another. When multiple measurements are taken on a given patient, that single patient can become a level of blocking factor, or block, with a total number of blocks equal to the number of patients. According to the checklist presented in the last video, blocking factors are typically considered random. For instance, if patients are sampled at random from a large population, and for a given treatment, patient-to-patient variation is nuisance variation, then it's reasonable to say that the patient factor is random. However, there is a caveat. Even if the chosen blocks represent only a sample from a large population of blocks, it is also necessary to account for how exactly the blocks have been selected. Consider the following example. An expanse of land has been divided into 16 small plots to test two types of fertilizer, A and B. To take into account that the yield from adjacent plots is likely to be similar, they decided to introduce 4 blocks of size 2 by 2 each. Within each block, the fertilizer is applied at random to the 4 plots. In the end, we have the fixed treatment factor with 2 levels and a blocking factor with 4 levels. We know that, for a given treatment, it's possible that the within-block responses are more similar to each other than the responses from distinct blocks. However, we have no idea how the blocks differ from one another. For all we know, the block-specific effect from the northwest block is exactly the same as the block effect from any other block. In other words, the blocks are not distinguishable. In that case, the blocking factor is considered random. Now consider a slightly different situation where there is an irrigation canal on the east side of the field. It's reasonable to assume that the amount of moisture in the soil is the highest next to the canal and the lowest on the opposite side of the field. In order to take that into account, we set up 4 blocks in vertical strips. The blocks are distinguishable by how far they are from the canal. In this case, the blocking factor is considered fixed. It's almost as if the blocking factor is another treatment that provides categorical information about the 4 levels of moisture: very low, low, medium, and high. The difference from the actual treatment, the fertilizer type, is that within each block, we can and we do assign the levels of fertilizer to the plots at random. As for the level of moisture, we can take it into account, but we cannot assign it to the plots in principle, not to mention random assignment. That distinction is subtle but very important because randomization is a pillar of experimental design. When effects of blocks or experimental units are treated as random, they might be called exchangeable. Exchangeability of random variables is a weaker form of IID property. If the random variables are independent and identically distributed, they are exchangeable. In the experimental design context, the blocks might be called exchangeable if, from our perspective, any block in the population could have taken place of each block in the observed sample. In that case, the block effect should be treated as random. As you can see, the task of drawing the line between fixed and random effects is nothing short of arduous. In the next video, I'd like to present another piece of the puzzle by discussing some cases where the choice makes no difference whatsoever.